After the last star stopped caring, there is a part of the universe that is not dark the way a room is dark when you turn off the light. It is dark the way a conversation is dark when it has been over for so long that no one remembers what it was about. You are somewhere comfortable right now, or trying to be. The hour is late enough that the sounds outside have changed register, lower, further apart, and the sleepy science channel is here because someone, maybe you, maybe a few thousand people who are also still awake right now, keeps coming back to it, and that means something to the people who make it. Something quiet, something that doesn't need to be said at full volume. The topic that's going to settle into this hour with you is not dramatic. It does not involve explosions or collisions or the violent theatre of the early universe. It involves absence. Specifically, it involves the kind of absence that has been there so long it has started to look like a choice. Out past the filaments, past the places where galaxies cluster along invisible threads of dark matter, past the dense nodes where thousands of galaxies crowd together like matter remembering that it prefers company. Out past all of that there are voids, enormous regions, hundreds of millions of light years across, and inside those voids, against everything the geometry seems to suggest, there are galaxies. Not many, not clustered, just there. This is where the chapter begins, not with what those galaxies are doing, but with how long they have been doing it alone. The universe is approximately 13.8 billion years old. That number is used so often in science writing that it has stopped landing with any weight, so set it aside for a moment. Think instead about what 13.8 billion years feels like as a duration of aloneness. Think about a galaxy that formed in the early universe, somewhere between 1 and 3 billion years after the Big Bang, in a region of space that was already emptying out. The filaments were pulling matter away. The great walls were organizing themselves somewhere else, and this galaxy just kept going, turning, producing stars, losing stars, turning some more, with nothing nearby to disturb it. The nearest neighbour, for some of these void galaxies, is 100 million light-years away. To put that in terms that are accurate but feel impossible, if the Milky Way were the size of a dinner plate, the nearest void galaxy's neighbour would be roughly 15 kilometres away. Not across the room, not across the city, across a significant portion of a country. And the void galaxy itself would be sitting alone on its dinner plate, turning slowly, completely unaware that the 15-kilometre away plate existed. Light from that neighbour has been travelling toward it for 100 million years and has not arrived yet. This is not metaphor. This is the geometry. What happens to a galaxy that never gets interrupted? The question takes time to answer because the answer is not what you might expect. The assumption, reasonable on its surface, is that isolation would produce something stunted. A galaxy without neighbours, without mergers, without the gravitational tidal forces that reshape spiral arms and trigger star formation bursts. Surely that galaxy would be quieter, smaller, less developed. In some ways it is. Void galaxies tend to be less massive than galaxies in denser regions. They have fewer satellite galaxies orbiting them. Their star formation rates are often lower. They are by certain measures behind. But behind is not the right word, because behind implies a destination, a standard, a normal rate of development that the void galaxy is failing to meet. What void galaxies have actually done is developed differently. not less, differently. They are bluer, on average, than galaxies in clusters. Blue in astronomy means young stars, hot stars, stars that formed recently. Void galaxies are still making stars at a steady, undisturbed pace, not in the bursts that cluster galaxies experience when they pass close to each other and their gas gets compressed and lit up all at once, but steadily, quietly, the way a fire burns when nobody's opening and closing the door. The cluster galaxy has a more dramatic history. More mergers, more interactions, more moments when everything changed quickly. The void galaxy has a longer, slower version of the same history. It is not that it missed out. It is that it was doing something else the whole time. The scientific study of void galaxies has a relatively short formal history, mostly because for a long time voids were defined by what they lacked, not by what they contained. A void was an empty region. By definition, there was nothing in it worth studying. The galaxies inside voids were sometimes called field galaxies, which is a polite way of saying they didn't fit the categories researchers were using. The shift began gradually. Studies in the 1990s and early 2000s started comparing galaxy properties across different environments systematically. The data that came back kept showing that where a galaxy lives matters as much as, and sometimes more than, what the galaxy is made of. Environment shapes evolution. This was not philosophically surprising. Biologists had known this about living systems for a long time, but the scale of it in cosmic structure was not fully appreciated until the surveys got large enough to compare thousands of galaxies across hundreds of millions of light years. The Sloan Digital Sky Survey, which began collecting data in 2000 and continued for years after, gave researchers the first genuinely panoramic view of the large-scale structure. When the data was rendered visually, the universe looked like a foam, or like the inside of a sponge, dense walls and filaments surrounding vast, mostly empty bubbles. The voids were not empty, they were just emptier, and inside them, faint, blue, steady, were the galaxies that had grown up without being interrupted. There is something specific about this kind of aloneness that is hard to move past without sitting in it for a moment. A void galaxy has been in its void for billions of years. The universe around it has been doing enormous things. Clusters merging, quasars flaring, black holes at the centres of galaxies growing to billions of solar masses, whole populations of stars forming and dying and seeding the next generation with heavier elements. All of this has been happening at full volume in the dense regions. The void galaxy has been receiving light from all of it for billions of years, arriving from every direction, old light, light that left its source before the void galaxy's current generation of stars even existed. It is surrounded by ancient signals it cannot respond to. The light arrives and passes through and continues on, and the void galaxy just keeps turning. Its stars go through their cycles. Its central black hole sits relatively quiet, not fed by the mergers and tidal disruptions that wake up the black holes in cluster galaxies. Its spiral arms, if it has them, are intact, not pulled and stretched by a passing neighbour. It is, for lack of a better word, undisturbed. Whether that is a loss or a gift is a question the void galaxy does not have an answer to. It is just a condition, a duration, a very long time of being exactly what it is, without anything nearby to suggest it should be something else. The chapter's end is not an arrival. It is a settling. Void galaxies will keep going. The voids themselves are expanding, not because of anything dramatic, but because the overall expansion of the universe is slightly faster in low-density regions, and the voids are the lowest density regions there are. They are getting bigger. The galaxies inside them are very slowly getting farther from even the distant walls that mark the void's edge. The aloneness is not static. It is a condition that is deepening, slowly, over billions of years, without any particular event marking the change. At some point the void will be large enough that the light from the nearest wall galaxy will be red-shifted beyond detection. The void galaxy will no longer be receiving signals it cannot respond to. It will just be turning in silence that is not a silence, because silence requires something to be absent, and by then there will be nothing expected. That is not an ending. That is just what comes next. The dust that was there before the word, dust meant anything. Inside a molecular cloud, somewhere in a spiral arm that has no name yet, because the civilization that would name it does not exist, a carbon atom that was forged in the core of a star that has already been dead for 3 billion years is attaching itself to other atoms, slowly, in the cold. The temperature here is around 10 Kelvin, 10 degrees above absolute zero. At this temperature, chemical reactions that would take milliseconds in a warm environment take years, decades. The cold does not stop chemistry, it just changes what chemistry has time to mean. The carbon atom bonds to hydrogen, then to oxygen, then to another carbon. A molecule forms, then another forms next to it, and another. Over thousands of years in the dark at temperatures that would register as essentially nothing on any scale a human body can feel, a grain of dust builds itself, one bond at a time, from the remnants of a star that went out before the Earth existed. This is where cosmic dust comes from. Not from erosion, not from decomposition, not from the kind of fine particulate matter the word dust implies when you find it on a shelf. It comes from dead stars and cold chemistry and time operating at scales that make the word slow sound impatient. There are several distinct types of cosmic dust, and the distinctions matter more than they initially appear to. Carbon-based grains, silicate grains, ice-covered grains, and polycyclic aromatic hydrocarbons, large carbon ring molecules that behave like very small solid particles, make up the bulk of what astronomers call dust. Each type forms in different environments, survives in different conditions, and interacts with light in different ways. Silicate grains form primarily in the cool outer atmospheres of dying stars, in the envelopes of asymptotic giant branch stars, which are stars in a late phase of their lives before they shed their outer layers entirely and collapse into white dwarfs. The silicon and oxygen and magnesium in these grains were produced by nuclear fusion inside those stars over millions of years, then carried outward into space on stellar winds as the star's life ended, and then, slowly, incorporated into the interstellar medium, the vast, diffuse material that fills the space between stars. Carbon grains form in a similar way but tend to come from different types of dying stars, those with a higher ratio of carbon to oxygen in their outer layers. When the chemistry of the star's atmosphere tips toward carbon-rich, the dust that forms tips with it. The difference between a silicate grain and a carbon grain is not just chemical. It is about what each grain can do. Silicate grains absorb and scatter ultraviolet light effectively. Carbon grains absorb across a broader range of wavelengths and are particularly good at absorbing the kinds of radiation that would otherwise destroy the fragile molecules forming inside molecular clouds. The dust does not simply float between the stars, it acts on the light that passes through it. It changes what survives. A grain of interstellar dust is, on average, about 1/10 of a micron across, 1/10 of 1/1,000,000th of a meter. At that scale, the grain is roughly the size of the wavelength of visible light, which is why dust scatters and reddens starlight the way it does. Shorter wavelengths, blue light, scatter more, while longer wavelengths, red light, pass through with less disruption. This is why distant stars look redder than nearby ones of the same type, and why the centre of the Milky Way, which we observe through thousands of light-years of dust-filled plain, is almost entirely invisible at optical wavelengths. The dust is not blocking the view out of obstinacy. It is simply doing what its size and composition cause it to do when light passes through it. Infrared telescopes changed everything. At infrared wavelengths, dust is not opaque. It is partially transparent. And so when the Spitzer Space Telescope, and later the James Webb Space Telescope, began observing in infrared, regions that had been closed off to observation opened up. Not just the galactic center, star-forming regions, embedded protostars, young stars still wrapped in the dust envelopes from which they were condensing. Dust that had been a barrier became a subject. The thing that blocked the view was also the thing worth looking at. The life cycle of a dust grain is long and interrupted. A grain forms in the outflow of a dying star. It travels into the interstellar medium, where it may spend hundreds of millions of years drifting, being slowly eroded by cosmic rays and the shock waves of supernova remnants, being incorporated into molecular clouds, being exposed to ultraviolet radiation at the cloud edges, being coated in layers of ice as molecules condense on its surface in the cold interior. In a dense molecular cloud, a grain accumulates a mantle of ice, water ice, carbon monoxide ice, carbon dioxide ice, methanol, a layered shell of frozen molecules that formed from the gas surrounding it. When a nearby star forms and begins to shine, the ice mantle starts to evaporate. The molecules that sublimate off the grain surface are released into the gas phase, where they can react with other molecules and build more chemical complexity. The dust grain is not just a passenger in this process. It is a surface, a catalyst, a place where chemistry happens that could not happen in the gas phase alone, because the gas phase does not give molecules the time and proximity they need to find each other and bond. Some of the most complex organic molecules detected in space, including amino acid precursors, have been found in regions where dust chemistry is active. The grain is not alive, but it is participating in the kind of chemistry that, under the right conditions, in the right sequence, over the right duration, leads toward the conditions that life requires. In 2020, a team of researchers confirmed that certain presolar grains extracted from the Murchison meteorite, a carbonaceous chondrite that fell in Australia in 1969, were older than the solar system itself. Silicon carbide grains specifically. Their age was determined by measuring the concentration of neon isotopes trapped inside them, products of cosmic ray bombardment that accumulate over time like a slow clock. The oldest grains dated to around 7 billion years ago. The solar system is 4.6 billion years old. These grains are older than the Sun by more than 2 billion years. They formed inside a star that died before our star was born. They drifted through the interstellar medium. They were incorporated into the molecular cloud that collapsed to form the solar system. They survived the formation of the Sun and the planets. They were swept up into a small rocky body in the asteroid belt. They rode that body for billions of years until its orbit shifted and it collided with Earth. They were collected by a research team in 1969. They were measured by scientists in 2020. The grain did not know any of this was happening. Knowing is not the point. The point is that the grain was there. Cosmic dust is not a relic. This is the part that takes the longest to settle properly. It is not ancient material sitting still in space, preserved from an earlier era. It is a continuous process. Stars are dying right now, shedding their outer layers, producing new dust. That dust is entering the interstellar medium right now. Molecular clouds are forming right now, accumulating dust, building the cold, dark environments where new stars and planets will eventually condense. Old dust is being destroyed by shock waves and radiation right now. Its atoms return to the gas phase to be incorporated into new grains later. The dust you would encounter if you could travel through the interstellar medium of the Milky Way is a mixture of grains with very different ages, very different origins, very different histories of where they have been and what they have been coated with. Some of those grains are older than the Sun. Some formed last century in the remnant of a nearby supernova. They do not look different from each other. At 1/10 of a micron, a grain is a grain. But inside each one is a record, isotopic, chemical, structural, of the specific environment in which it formed and the specific sequence of environments through which it has travelled. The universe keeps records in the smallest things, not deliberately, just because matter holds on to its history in ways that time alone cannot erase. A grain of dust that formed 7 billion years ago in the atmosphere of a dying star is still, at the atomic level, carrying the signature of that star's specific chemistry. The record is there, it is very small, and it is very, very old. A galaxy that has no idea you exist. Something is about to become clear, not in a dramatic way. In the way that a thing you have been looking at for a while finally resolves into what it actually is. The galaxy does not know you are watching it. This is not a poetic observation. It is a structural fact about the relationship between observers and the things they observe at cosmological distances. The light you would be receiving from a void galaxy, 100 million light years away, left that galaxy 100 million years ago. The galaxy you are looking at is not the galaxy as it is now. It is the galaxy as it was. By the time any signal from your observation, any light, any particle, any influence of any kind, reached that galaxy, both you and the galaxy would be unrecognizably different from what you are in this moment. The relationship is one-directional, and even the direction is already over. What does it feel like, in the body, to understand this? Not to process it intellectually, but to actually let it land. There is something that happens as the chest, or behind the eyes, when a scale becomes genuinely real, rather than merely acknowledged. You can know that a void galaxy is 100 million light years away, and feel exactly nothing. That is normal. The human body did not develop instruments for feeling cosmological distances. It developed instruments for feeling whether the branch underfoot will hold weight, whether the voice in the dark is friendly, whether the food is safe. The scale of the universe is outside the body's registration range, completely. So the body does not feel it. It just knows it. In the thin, verbal, easily forgotten way it knows things it has been told. But there is another way to feel it, and it goes like this. Think about the last time you were genuinely completely unobserved, not unnoticed, unobserved in the deeper sense, not being registered by any other consciousness, not mattering to any other awareness, existing in a bubble of complete independence from any external reference point. It is harder to access than you might think. Even alone in a room, the body is aware of the possibility of observation. It holds itself differently when it believes nobody is watching. The loosening that happens when genuine solitude arrives is almost physical. A void galaxy has been in that state for billions of years. It is not relaxed because relaxation requires a prior tension. It is simply operating without any reference to anything outside itself. Its stars go through their cycles because that is what stars do. Its gas cools and collapses into new stars because that is what gas does under gravity. Its central region processes whatever falls into it because that is what central regions do. None of this is in response to anything. None of this is happening because of or in spite of anything nearby. It is just happening because it is the kind of system that does these things, and nothing has interfered. The middle section here asks something of you. It asks you to sit with the idea that evolution, in the most general sense, the way things change over time in response to their environment, is something that void galaxies experience very slowly and differently, not because they are incapable of change, but because the environment that drives change in cluster galaxies barely exists for them. When two galaxies in a cluster pass close to each other, their mutual gravity does things. It distorts their shapes. It compresses gas clouds and triggers bursts of star formation. It can strip material from the outer regions of each galaxy, leaving trails of stars and gas in the space between them. It can, over multiple passes, cause galaxies to merge entirely, producing a new, larger, rounder galaxy from the collision of two spiral ones. This is common in clusters. Astronomers have catalogues of interacting galaxies, merger remnants, galaxies in the process of being pulled apart. The universe in dense regions is a place where things collide and reshape each other constantly, on timescales that are long by human standards but rapid by cosmic ones. A void galaxy does not have this. Its evolution is driven primarily by internal processes. The gas it started with, the dark matter halo it grew inside, the stars it formed from its own material, the supernova from those stars that inject energy back into the gas and regulate how quickly the next generation forms. It is a closed system in a way that cluster galaxies are not perfectly closed. Gas can fall in from the surrounding void environment, and void galaxies do interact gravitationally with the distant walls and filaments, weakly, slowly, but closed enough that the dominant processes are internal. This means the void galaxy is, in a sense, a cleaner experiment. Less noise from the environment, more signal from the internal physics. Astronomers studying void galaxies are, in part, trying to understand what a galaxy does when left to itself, which tells you what the internal processes contribute, separate from the environmental ones. What the data shows is this. Void galaxies are, on average, bluer, lower in mass, higher in gas fraction, and more regularly shaped than their counterparts in denser environments. They have had fewer mergers. Their star formation is steadier, lower in peak intensity, longer in duration. Their central black holes are less active. Their stellar populations are on average younger, meaning they are still forming stars rather than having used up their gas reserves in early bursts. They are, in the language astronomers use without always intending it literally, younger looking. Not younger, looking younger. The distinction matters. A void galaxy can be just as old as a cluster galaxy. They formed in the same early universe, but the cluster galaxy burned fast and bright and used up its star-forming gas reserves quickly, heated and exhausted by interactions and mergers, and now may be a red, dead elliptical. All old stars, no new ones forming, fading over billions of years. The void galaxy is still going, still blue, still making stars, still in the long middle part of its life that the cluster galaxy rushed through. This is the thought that keeps coming back, from different angles, each time a little different. The void galaxy is not behind. It is not ahead. It is just somewhere else in a process that does not have a universal schedule. The cluster galaxy and the void galaxy started at roughly the same time, in the same universe, with roughly similar starting materials. They look different now because of where they happen to be. Not because of anything they did, not because of any choice or trajectory or priority, just location. Just the accident of which part of the large-scale structure they condensed in, billions of years ago, before the voids were even fully voids. The galaxy you're looking at, 100 million light-years away, already finished, already resolved, or not, into whatever it became in the time since that light left. You are watching a moment that is over, from a distance that makes response impossible, learning something about a system that developed entirely without reference to you or anything like you. That is not lonely exactly, but it is something, the largest thing that has a name. You already have a sense of how large the universe is, or you think you do. The sense is wrong, not because you have been given bad information, but because the information is the right information, and the human perceptual system is simply not built to receive it at full size. The number arrives, gets acknowledged, and then sits in a part of the mind that stores acknowledged but not felt things, alongside the number of cells in the body and the age of the Earth, and the distance to the nearest star. Known, not felt. So let's try something different with the Hercules Corona Borealis Great Wall. The Hercules Corona Borealis Great Wall is a large quasar group, a region of space where an unusually high concentration of quasars exists relative to the surrounding volume. Quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes actively consuming material. They are among the brightest persistent objects in the universe, visible across billions of light years. The Hercules Corona Borealis Great Wall was identified in 2013 by analysing the spatial distribution of gamma-ray bursts, which are themselves associated with the most energetic events in the universe and serve as tracers of the large-scale distribution of matter at cosmological distances. Its estimated extent is roughly 10 billion light-years across. The observable universe is approximately 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall spans, very roughly, more than a tenth of that. If you placed it at the centre of the observable universe, it would reach more than 5 billion light-years in every direction. Here is the problem. According to the cosmological principle, one of the foundational assumptions of modern cosmology, the universe is, on the larger scales, homogeneous and isotropic. This means roughly the same in all directions and roughly the same in any region you sample, provided the region is large enough. The universe should not, at large enough scales, have enormous structures. The density fluctuations that seeded the large-scale structure, the tiny variations in the density of the early universe that gravity then amplified over billions of years into filaments and walls and voids, should not, according to current models of structure formation, have had time to produce structures larger than about 1.2 billion light-years. That is the theoretical upper limit for how large a coherent large-scale structure can be, given the age of the universe and the rate at which structure forms under gravity. The Hercules Corona Borealis Great Wall is approximately 8 to 10 times larger than that limit. This is either a problem with the structure, a problem with the theoretical limit, or a problem with the observation. Possibly some combination of all three. Researchers have debated whether the structure is genuinely coherent, whether it represents a real physical overdensity, or whether it is a statistical artifact of the gamma-ray burst sample used to identify it. The sample is relatively small, and gamma-ray bursts are not uniformly distributed in time. They were more common in the earlier universe, which complicates using them as traces of structure at different epochs. The uncertainty is real, and the narrator does not want to give the impression that it is not. This is not a settled case. The Hercules Corona Borealis Great Wall may be exactly what it appears to be, or it may be a structure whose apparent size shrinks under more refined analysis, or it may be something in between. Real, but somewhat smaller, real but less coherent, real but differently shaped than the initial identification suggested. What the structure represents, regardless of how the measurement debate resolves, is a genuine confrontation with scale. 10 billion light-years. A light-year is the distance light travels in a year, moving at roughly 300,000 kilometers per second. 10 billion of those. The numbers stack up and the mind does the requested arithmetic and then puts the result down and moves on because there is nowhere to put it that makes it feel like anything. The universe has been expanding for 13.8 billion years. Light that left a source 10 billion light-years away, left that source when the universe was only a few billion years old. The structure you're looking at, or rather, the structure that astronomers identified using light that has been travelling for billions of years, is a snapshot of something that existed in the early universe, when everything was different, when the expansion rate was different, when the clustering of matter was still in its earlier phases. And even in those earlier phases, this structure, if it is what it appears to be, should not have had time to become what it is. The universe has a speed limit for structure formation. Gravity moves fast, but the universe expands, and expanding space dilutes gravitational influence over time, and the net result is that there is a theoretical maximum size for structures that gravity can build in the time available. The Hercules Corona Borealis Great Wall exceeds that maximum, which is a polite way of saying that it is, according to the standard model of cosmology, currently impossible, and yet the data, cautiously interpreted, it exists. The thing about confronting a structure that should not exist is that it does one of a small number of things to your understanding of the model that said it should not exist. It forces you to look at the model differently, not to discard it, because the model works extraordinarily well for almost everything else, but to look at it the way you look at a map when the road you're on does not match the road on the map. Either the map is slightly wrong, or you have misread it, or you are somewhere the map maker did not go. Cosmologists have been in this position before. The discovery that the expansion of the universe is accelerating, confirmed in 1998, was deeply inconsistent with the prevailing model at the time. The response was not to discard general relativity. It was to add something to the model, dark energy, a term for the unknown mechanism driving acceleration, and to update the model accordingly. The Hercules Corona Borealis Great Wall is currently waiting for its update. The update may be a refinement of the observation, showing the structure is smaller or less coherent than initially measured. It may be a refinement of the theoretical limit, showing that under certain conditions structure formation can proceed faster than the standard model allows. It may be something more significant than either. The narrator genuinely does not know which of these it will be. The literature is in progress. The data continues to arrive. In the meantime, the structure sits there, in a part of the sky that covers portions of Hercules and Corona Borealis, 10 billion light-years wide, waiting. The honest statement is this: the largest named structure in the observable universe may be larger than the universe should have been able to make. That sentence is not dramatized. It is not inflated for effect. It is the current provisional contested state of the observation, and it sits at the center of this outline not because it is the most certain thing being discussed, but because it is the most generative kind of uncertain thing, the kind that does not undermine the surrounding knowledge but pressures it, asks it to account for something it currently cannot fully account for, and waits. The scale is real, the uncertainty is real, and somewhere out there, a structure that should not be possible is just sitting there, which is either fine or it isn't. Dust knows how to block a secret. Something was hidden. For most of the 20th century it was hidden in plain sight, which is a strange phrase when you consider that the thing doing the hiding was not invisible. It was just very, very thick. The zone of avoidance. Astronomers gave it that name formally, and the name is accurate in both the clinical and the colloquial sense. It is the region of the sky where our own galaxy's plane, the dense dust-filled disk of the Milky Way, sits directly in the line of sight, and because the dust in that plane is optically thick at visible wavelengths, meaning light at those wavelengths simply does not pass through it cleanly, the zone of avoidance was, for optical astronomy, a wall. Behind that wall, across roughly 20% of the sky, was anything. Galaxies, galaxy clusters, superclusters, large-scale structures, all of it blocked by the dust of our own home, the way you cannot see the countryside beyond a frosted window. The name zone of avoidance was not meant to imply that astronomers were choosing to avoid it. It referred to the fact that on early galaxy catalogues, this region was simply blank. Other galaxies were plotted across the celestial sphere, and then there was a band centered on the galactic plane where the catalogue went silent. Galaxies appeared to avoid that region, not because they did, but because the dust prevented us from seeing them. Behind the wall, galaxies were doing what galaxies do. They were clustering along filaments. They were pulling on each other gravitationally. They were part of the large-scale structure that astronomers were trying to map, and they were completely absent from the map. Not because they were not there, but because the dust of the Milky Way had been in the way since before anyone thought to look. The opening came gradually, from multiple directions at once. Radio waves pass through dust. They have much longer wavelengths than visible light, and the dust grains that scatter and absorb optical wavelengths are essentially transparent to radio. Radio telescopes looking through the zone of avoidance began detecting galaxies in the 1970s and 1980s. The H.I. Parkes All-Sky Survey, and later other systematic radio surveys, began to reveal the distribution of hydrogen gas in galaxies hidden behind the plane, which allowed astronomers to identify galaxies by their gas content even when the stars themselves were invisible. Near-infrared light also penetrates dust more effectively than optical light. Not as completely as radio, but enough to dramatically reduce the obscuration. Near-infrared surveys of the zone of avoidance in the 1990s and 2000s began recovering galaxies that optical surveys had missed entirely. The COBE satellite, the 2MASS survey, and targeted observations with ground-based infrared instruments all contributed to gradually filling in the blank on the map. What they found mattered enormously for understanding the dynamics of the local universe, the Great Attractor. It had already been identified through its effects before anyone saw what it was. In the 1970s and 1980s, astronomers studying the motions of galaxies noticed something odd. The Milky Way, along with the local group, along with the Virgo supercluster, was moving. Not just participating in the general expansion of the universe, but moving with a peculiar velocity relative to that expansion, a bulk flow of roughly 600 kilometers per second toward a specific region of the sky. That region was in the zone of avoidance. The gravitational pull responsible for this motion required a mass concentration of somewhere between a few 100 trillion and a quadrillion solar masses. Something enormous was behind the dust, pulling the local universe toward it, and nobody could see it. The infrared and radio surveys, when they finally penetrated the zone of avoidance deeply enough, found it. Not a single object. The Great Attractor is not a single galaxy or cluster, but a broader overdensity centered around the Norma cluster, a rich galaxy cluster approximately 250 million light-years away, embedded in a larger supercluster. The Hydra Centaurus supercluster, the Norma cluster, and several surrounding structures appear to be the main contributors to the gravitational pull that has been steering the local universe for billions of years. And the dust of the Milky Way had been sitting in front of it the whole time. There is something specific about this particular discovery that is different from other large-scale structure findings. Most discoveries in cosmology involve seeing something that was not previously visible. A new telescope resolves a new class of objects, or a new wavelength regime opens up a new population of sources. This discovery involved realizing that a force had been acting on us, on our galaxy, our neighborhood, our local cluster, for longer than the Earth has existed, and we had not known what it was because our own home was in the way. The dust of the Milky Way, the remnants of stars that died before the sun formed, had been blocking our view of the thing that has been pulling us through space for billions of years. We were being moved by something we could not see because we were looking through ourselves. The observation corrected itself slowly, instrument by instrument, wavelength by wavelength, until the thing behind the wall came into focus. Not fully. Parts of the zone of avoidance remain difficult even now, and the precise mass distribution behind the galactic plane is still being mapped with greater resolution. But the main structure is known, the direction is confirmed, the pull is accounted for. The wall came down gradually, which is how most walls come down, not in a moment but in a slow accumulation of better tools and more time, and a willingness to keep looking at a blank space on the map and ask what is actually there, what empty actually costs. The void is expanding right now, and it is doing it without anyone asking it to. Not the universe, though the universe is also expanding, and the two expansions are related in a way that takes a moment to untangle. The void itself, the specific region of low-density space that has been emptying out for billions of years, is getting bigger at a rate that is slightly, measurably different from the expansion of the surrounding denser regions, and that difference is not incidental, not a rounding error, not a detail that matters only to specialists working at the edges of precision cosmology, but a physical fact that connects the geometry of empty space to the mechanism that is pulling the entire universe apart. The mechanism is called dark energy, provisionally, because it is not understood deeply enough to deserve a more specific name, and the way it operates in cosmic voids is one of the cleaner places to look at it, because voids are the regions where matter is least dense, and therefore where the expansion that dark energy drives is least complicated by the gravitational resistance that dense matter provides. Think of it this way, though imperfectly. A region of space with a lot of mass in it is also a region of space where gravity is working hard against expansion. The mass pulls on itself, slows the local expansion rate, keeps things closer together than they would otherwise be. A void with very little mass offers much less resistance. The expansion in a void runs slightly ahead of the average, not by much, but by enough to measure. The integrated Sachs-Wolf effect, one of the methods used to detect this, involves looking at the cosmic microwave background, the oldest light in the universe, and watching what happens to individual photons as they travel through voids and through dense structures. A photon passing through a dense structure in a universe without dark energy would gain energy entering the gravitational well and lose exactly the same amount leaving it, the net effect being zero. But in a universe where dark energy is causing the structure to become less dense while the photon is crossing it, the exit is slightly less steep than the entry, and the photon exits with a tiny net gain in energy, slightly bluer than it entered. Conversely, a photon passing through a void loses slightly more energy than it gained, slightly redder at the exit than at the entry, slightly. Everything in this chapter is about things that are happening slightly. The measurements are real and confirmed by multiple methods, but the signals are not large. They are the kind of signals that require correlating the positions of thousands of galaxy clusters and voids with temperature fluctuations in the cosmic microwave background that are themselves only millionths of a degree from the average. The void is expanding slightly faster. The photons are slightly redder or bluer, depending on the geometry. The measurements agree slightly with each other, and from this accumulation of slightlies, cosmologists extract one of the strongest independent lines of evidence that dark energy exists, and that it is causing the expansion of the universe to accelerate. What costs the void, if you hold the question loosely, is density. The void is paying out density over billions of years, slowly losing whatever matter it started with to the gravitational pull of the surrounding filaments and walls, matter draining away from the interior toward the edges the way water drains from a shallow bowl, tilted at a very slight angle over a very long time. The galaxies in the void, the ones discussed earlier in this outline, are not draining away. They are gravitationally bound to their own dark matter halos, which anchor them in place even as the void around them expands. But the diffuse gas, the intergalactic medium that fills the space between void galaxies, does slowly move. It moves toward the filaments. It feeds the cluster galaxies at the nodes. It participates slowly in the redistribution of matter from empty regions toward dense ones that has been happening since the large-scale structure began to form. The void is not becoming emptier because of dark energy directly. The matter drain is gravitational, the ordinary pull of dense structure on diffuse matter. The dark energy effect is different. It accelerates the expansion of the void itself, meaning the void grows faster than it would in a universe without acceleration. The matter inside the void does not move faster toward the edges. The edges move away from the center faster, taking the whole volume of emptiness with them. The result, accumulated over billions of years, is a universe where the voids are getting larger, the walls and filaments are getting denser, and the contrast between full and empty is increasing. The universe is becoming more structured over time, not less, at least locally. The density contrasts between voids and filaments are growing, even as the universe as a whole expands and dilutes. This will not continue indefinitely. At some point in the far future, if dark energy continues to accelerate expansion, even the filaments and walls will be pulled apart. The clusters will disperse. The galaxies within them will separate beyond the range of gravitational communication. Eventually, in the very far future scenarios, even individual galaxies may be disrupted, their stars spread across expanding space until no structure remains at any scale. But that is very far away. For now, the voids are expanding, the walls are growing denser, and the universe is arranging itself into an increasingly elaborate structure of full and empty, like something that has been sorting itself quietly for 13 billion years and is not finished yet. What empty costs is itself. Over enough time, a void pays out its own contents until it is as empty as it is possible to be, and then it keeps expanding anyway, taking the emptiness with it, growing the nothing into a larger nothing, which turns out to be what nothing does when you give it enough time and a slight push from the geometry of space-time. Grains of something older than the solar system. The meteorite fell in 1969. It came down near Murchison in Victoria, Australia. A fireball in the morning sky, a sound, then pieces of rock on the ground, still warm, smelling of something organic and sharp. Sulfur compounds and carbon chemistry that had been sealed inside since before the Earth existed. People collected the pieces. Researchers studied them. The Murchison meteorite became one of the most analysed objects in the history of planetary science. It is a carbonaceous chondrite, a type of meteorite that preserves material from the early solar system, including material that predates the solar system entirely. Inside the Murchison meteorite, embedded in its matrix, there are grains. Not all grains are the same. Most of the material in the meteorite formed within the solar system from the cloud of gas and dust that collapsed to form the Sun and its planets 4.6 billion years ago. But some grains have isotopic signatures that do not match anything that formed in the solar nebula. Their ratios of silicon, carbon and noble gas isotopes point to origins in stellar environments that existed before the Sun was born. These are presolar grains. They are older than the solar system. The silicon carbide grains in the Murchison meteorite carry neon inside them, specifically neon-21, which forms when cosmic rays, high-energy particles streaming through interstellar space, bombard silicon carbide over long periods of time. The longer a grain is exposed to cosmic rays in interstellar space, the more neon-21 accumulates inside it. The accumulation is a clock. In 2020, researchers at the Field Museum in Chicago measured neon-21 concentrations in presolar silicon carbide grains from the Murchison meteorite, and used those measurements to determine how long the grains had spent in interstellar space before being incorporated into the solar nebula. The oldest grains they measured had been travelling through interstellar space for around 2 to 3 billion years before the solar system formed. Adding that to the age of the solar system gives a formation age of roughly 6 to 7 billion years ago. The Sun is 4.6 billion years old. These grains are older by more than 2 billion years. Let that sit in its actual dimensions for a moment. 2 billion years is longer than the Earth has had complex multicellular life. It is longer than the Cambrian explosion, the great oxygenation event, the formation of the first continents. It is longer than almost any geological feature visible on Earth's surface today has existed in its current form. 2 billion years before the Sun formed, these grains were already old enough to have been travelling through the interstellar medium for billions of years. They were born in a star that lived its life and died and scattered its material before any part of what would become the solar system had begun to coalesce. That star does not have a name. It exists only as a signature in the isotope ratios of a grain too small to see with the naked eye, recovered from a piece of rock that fell from the sky over rural Australia on the morning of September 28th, 1969. What did the grain do in the time between the death of its parent star and its incorporation into the solar nebula? Mostly it drifted. It moved through the interstellar medium, carried on stellar winds and pressure from radiation, slowly changing direction under the influence of magnetic fields and the gravitational gradient of the galaxy. It was exposed to cosmic rays, which gradually built up the neon-21 inside it that would eventually serve as evidence of its age. It may have passed through molecular clouds, accumulating ice mantles that would later sublimate away. It may have come close to forming stars, been swept up in infalling material, and then expelled again when the protostar's jets cleared its surrounding envelope. It survived. Not through any property of survival instinct, but through a combination of size, composition, and geometric luck, being in places where the processes that destroy interstellar grains, shock waves, intense radiation, thermal sputtering, happen to miss it. Silicon carbide is a relatively stable compound. It holds its structure under conditions that would destroy less stable grains. It is the reason presolar silicon carbide grains are among the most commonly found presolar species in meteorites, not because silicon carbide grains are the most common grains in the interstellar medium, but because they survive better than others and are therefore overrepresented in the survivors. The grain you are imagining now is not a typical interstellar grain. It is a survivor specifically because of what it was made of, and the fact that it survived is the only reason we know it existed. This is the part that arrived quietly and keeps expanding the more you look at it. The grain in the Murchison meteorite is not a fossil. A fossil preserves the shape of a living thing. This grain is the actual material, the actual atoms, arranged in the actual crystal structure that formed in the atmosphere of a dying star 7 billion years ago. The atoms in it were processed in stellar nuclear synthesis, expelled into space, travelled for billions of years, survived incorporation into the solar nebula, survived the formation of the sun and the planets, were swept into an asteroid that spent billions of years in the belt between Mars and Jupiter, fell to Earth, lay on the ground in Australia, were picked up, shipped to laboratories, and were measured. The measurement happened in 2020. The atom in the grain is the same atom that formed in the star, not a copy, not a reconstruction, not an inference from a trace or a signal or an isotopic ratio. The atom itself still carrying the specific nuclear configuration that identifies it as the product of a specific type of stellar nucleosynthesis in a specific type of stellar environment that existed more than 7 billion years ago, is sitting in a laboratory somewhere right now, possibly in more than one laboratory, certainly in more than one paper, and nobody fully knows what to do with that except to keep looking at it and write down what it says. The filaments, nobody asked about. Between the clusters and the voids, there is a geometry that nobody named until they had to. The filaments, threads of dark matter and baryonic gas, hundreds of millions of light years long in some cases, along which galaxies arrange themselves like condensation on a wire. They are not the densest structures in the universe. They are not the most extreme. They do not contain the most massive clusters or the most energetic events. They exist mostly as the connective tissue between things that seemed more important, and for a long time that is what they were called. Connective tissue. The parts between the interesting parts. This chapter is not interested in that framing. The filaments formed from the same density fluctuations that formed everything else in the large-scale structure. The tiny variations in the density of the early universe, imprinted at the level of quantum fluctuations and then inflated to cosmic scales by the period of rapid expansion called inflation, seeded the gravitational collapse that produced all structure. Dense regions collapsed faster under their own gravity, forming the first dark matter halos. Less dense regions collapsed more slowly. The least dense regions, the voids, stopped collapsing entirely and began to expand as the universe's accelerating expansion outpaced their weak internal gravity. The filaments are what happened along the edges between these regions. Material that was slightly overdense along certain directions, slightly underdense in the perpendicular directions, collapsed preferentially along the direction of highest density, forming sheets, and then the sheets collapsed along their densest axis, forming filaments. The geometry of large-scale structure, the foam-like pattern of voids surrounded by walls and filaments connecting at dense cluster nodes, emerges naturally from gravity acting on the initial density field. You do not need special ingredients. You need gravity, dark matter, time, and the right initial conditions, and you get the cosmic web. The filaments carry gas. Not just the galaxies strung along them, but a diffuse, warm-hot gas that fills the space between those galaxies, called the warm-hot intergalactic medium, or WIM. This gas has temperatures between roughly 100,000 and 10 million Kelvin, heated by the gravitational collapse that formed the filament and by shock waves from galaxy formation processes within it. It emits primarily in soft X-rays and in the UV part of the spectrum. For a long time, this gas was very difficult to detect directly. Its density is low enough and its temperature is specific enough that the signal is faint and easily confused with other sources. The WIM matters for a specific reason that goes beyond its own properties. Cosmological models predict that the majority of ordinary matter in the universe, not dark matter, but the baryonic matter made of protons, neutrons and electrons that makes up everything visible, should be located in the warm, hot intergalactic medium of the cosmic web, not in galaxies, not in clusters, in the filaments, in the diffuse gas between galaxies, invisible at optical wavelengths, detectable only with X-ray and UV telescopes looking for faint absorption features in the spectra of distant background sources. For a period in the late 20th century, this was called the missing baryon problem. Counting up all the visible matter in galaxies and clusters accounted for only a fraction of the baryons predicted by models of Big Bang nucleosynthesis. The rest were, in some sense, missing. The WIM in the filaments was the leading candidate for where they were. Observations over the past 2 decades, particularly with the XMM Newton and Chandra X-ray observatories, have gradually confirmed that the filaments do contain this warm-hot gas, and that the WIM accounts for a significant portion of the missing baryons. The matter was not missing. It was in the filaments, in a form that was hard to see. The question was answered by learning to look differently. There is something about the scale of the filaments that resists easy visualization. A filament might be 50 million light-years long and a few million light-years across. The galaxies within it are distributed unevenly, clustering more densely where the filament intersects another filament or meets a cluster node. The dark matter halo of the filament, the invisible gravitational skeleton on which the gas and galaxies hang, extends even further than the visible material. The filament is, in a sense, mostly dark matter, with a visible lining of gas and galaxies. Walking through a filament, if such a thing were possible, would not feel like walking through something. The density is still extremely low by any terrestrial standard. The intergalaxy distances within a filament are millions of light-years. The filament is a structure defined at the scale of the universe, not at the scale of anything with walls you can touch. Its geometry is apparent only when you are far enough away to see it as a thread, which requires being far enough away that the individual galaxies within it are points of light. The web of filaments connecting every cluster in the observable universe is the largest coherent structure that has a continuous physical existence. The Great Wall and the Hercules Corona Borealis structure are impressive, but they are overdensities within the web. Concentrations of nodes and filaments in a particular region. The web itself is the thing those concentrations are parts of. It covers the universe, not metaphorically. It connects, through chains of filament and node, every galaxy cluster that has enough mass to be considered a node in the structure. The gas flows along the filaments toward the cluster nodes. Galaxies form preferentially at the nodes and along the densest parts of the filaments. The voids are defined by their absence of filaments, which is to say they are defined by the web's edges. The universe is, at its largest scale, a web. The clusters are the heavy nodes. The galaxies are the luminous beads. The filaments are the threads. The voids are the open spaces where the threads did not go. And everything that is visible, every galaxy ever observed, sits somewhere on that web, which has been assembling itself from gravity and dark matter and time since the universe was a few 100 million years old. The filaments are not the parts between the interesting parts. They are the parts the interesting parts are attached to. They were always the structure. It just took a while to see them as such, and longer still to look at them directly and ask what they contained, and to find, in the warm, invisible gas between their visible galaxies, most of the ordinary matter in the universe, waiting in the place nobody had thought to look, relaxing into the scale. Something is about to stop being frightening, and the chapter is about what happens at that threshold. Not peace, exactly. Not understanding in the full sense. Something more like the moment when a very loud sound has been going on for long enough that you stop flinching at it. Not because it has gotten quieter, but because the body has finished treating it as an alarm. The scale of the universe is like that loud sound. At first, the numbers produce something, a kind of vertigo, a slight breathlessness at the distance between galaxies, at the age of presolar grains, at the width of structures so large they should not exist. The brain treats these numbers as threats to its spatial model of the world, and the body registers something, not quite fear, but adjacent to it, and then, if you sit with the numbers long enough, the registering just stops. The numbers are still there. They are still accurate. They have not become smaller. But the alarm has run its course. This is not a failure of comprehension. It is a feature of the way the brain handles information outside its evolved range. The human brain did not develop the capacity to feel the difference between 100 million light years and 1 billion light years because no difference of that kind ever mattered for survival. The brain developed the capacity to feel the difference between 20 meters and 200 meters, between a sound that is approaching and one that is receding, between a face that is tense and one that is relaxed. These were the scales at which survival operated. Cosmological distances exist entirely outside that range, so the brain does what it does with other things outside its range. It places them in a category of known things, large, far, old, and stops trying to feel them and starts just storing them. Acknowledged, filed, not felt. There is a point at which this filing stops producing frustration and starts producing something else. The something else is hard to name without making it sound more significant than it is. It is not enlightenment. It is not a spiritual state. It is closer to the feeling of being in a large empty building late at night, when the scale of the space around you has stopped feeling threatening and started feeling simply true. The building is as large as it is. The space is what it is. You are where you are in it. None of this requires a response. The universe is approximately 93 billion light years in diameter. This is true. The Hercules Corona Borealis Great Wall is approximately 10 billion light years across. This is provisionally true, contested, probably in that range. A presolar grain in the Murchison meteorite is older than the Sun by more than 2 billion years. This is true. A void galaxy has been turning without a neighbour for billions of years. This is true. These facts do not require anything from you. They are not challenges. They are not tests. They are just descriptions of what is happening at scales you will never inhabit. And at some point, the knowing of them stops producing a demand for a response and starts producing something closer to rest. The word relaxing is in the title of this video. This chapter is the only one that addresses it directly, and only briefly, because directly addressed the quality dissolves. It is better approached obliquely, the way this chapter has been approaching it, circling the idea of scale-induced stillness without naming it as a goal, or a method or a practice. The facts about void galaxies are relaxing not because they are comforting. They are not. A galaxy evolving alone for billions of years, developing without any external reference, its light arriving at your eye 100 million years after it left, the relationship entirely one-directional and already over. This is not a comforting fact, but it is a fact that, held long enough, produces a very specific kind of cognitive quiet, the quiet of something too large to worry about, something happening at a scale so far outside the range of anything you can affect or anything that can affect you, that the usual machinery of anxiety simply has nowhere to attach. This is different from peace. Peace implies resolution. This is more like scale immunity. The universe is doing something very large and very old and very indifferent to your particular Tuesday. And knowing this precisely and completely is, for some people, at some hours of the night, exactly enough.